Hello everyone. So now we are actually at our second half of the course, and the topic that we're going to discuss today will be on line integral. So the important part of what we need to know about line integral, all right, so let's see what we're going to explore here today. So first of all, we're going to discuss about line integral, all right, in its 2D form and 3D form, two-dimensional, three-dimensional. So if you can guess it, two-dimensional, just that the vector field will actually involve only two axes, this one three axes, right? And then of course we also need to know a little bit about the fundamental theorem, so that's what we're going to discuss as well. So one on the fundamental theorem, and then something that's very closely related to line integral, the curl. So this is something that you're going to look at also today. And lastly, we're going to look at how this FDS that you see here is different from the F dot T ds. So as you can see that one here, this F here is actually denoted by the bar on top. So this actually indicates vector field, if you still remember. So there are like a little bit of a difference when it comes to us solving this. So we're going to look at that later on, all right? So let's get started. I mean, one of the most important thing that we need to know about when it comes to line integral, all right? So that would be to parameterize the equation that is given to us for a given curve. All right, so that's the thing that you want to know. So if you remember again, when we did surface integral not too long ago, remember we have the parameter equation and so on. So it's all this kind of thing that you want to remember. All right, so it's very important to parameterize the equation, but later on when we do the question, you will be able to see it clearer. So let's start with the formula first, all right? So if we are supposed to find a line integral of a function, let's say the function is given by x and y in its variable along curve C, all right? And the formula then will be, so we can just say that probably, let's say this is a function of xy, all right? And we have this curve C, let me just denote it as C, and this is from A to B, all right, which means A is the beginning point and B is the ending point. So the way that we write this for a line integral, all right, will then be f of xy ds. All right, and how do we know about this ds? So as you can remember, even when you were doing your surface integral, you actually deal with the limit of the lower limit and upper limit of the integral of two sides, right? But since this is line that we're talking about, so we actually have this curve C, and therefore what we have to do to get these lengths over here will just basically be integrating the curve C function, and the curve C function here is given by your f of xy, and this ds, if you can just remember and just relate it, this ds will just basically indicate the length from here all the way to here. All right, so basically it just means that it's the whole length. So I can see that this whole thing here is actually my ds. All right, and I'm just going to move this up a little bit. And so that would be the further derivation of this equation here will then look something like this. All right, we will have an integral of lower limit a to upper limit b, all right, according to the interval. And then we have f of xt and yt. So remember that we would have parameterized the equation of the curve already. That's why you actually see in this form here, and then multiply it by our r bar prime, all right, of dt. So see that everything has been changed into its variable t, and this actually just indicates the magnitude. I'm going to explain a little bit on how we get to this one here. All right, so say earlier we have talked about parameterization and all that, right? So from this equation that you just see, let's explore the second term here a little bit. All right, so say we want to parameterize, all right, the curve as a vector function. Just going to write this as this. All right, so in this case, just in case you're wondering what's this r bar, all right, so r bar will then be the parameterized equation that we have performed on our function of xy. So basically what it means is that we actually take this function of xy and then we convert it into its parameterization method, and we are actually going to get its x component in terms of t and its y component here in terms of t as well. All right, and once we have parameterized this is actually just the r function. I'm just indicating this as r, but it's actually just the parameterized function of my earlier function in terms of x and y. And then after that, you see this thing over here. So if I am going to get my r prime and get its magnitude of it, indicated by this double vertical line here. All right, so if you remember, the r prime basically just means that we are getting the dx of dt and the dy of dt, right? So we're differentiating it with respect to x and y. And then, all right, let's just test what you still remember about your magnitude. So for magnitude, remember what we do is that we actually get coefficient of my x and y. And what do we do? Can you recall? So remember that we actually square each component and then we sum it up and then we get a square root of it. And that will be our r prime t in terms of the magnitude, which is indicated by these two vertical lines here. All right, just so happen, so see to that whatever that has been indicated over here in this box here, do notice that it's actually in terms of x and y, right? So what does this mean? This actually means that our curve is in its 2D dimension. Basically, it means that your curve lies on only two axes. It can be xy, yz, or zx, for example. So just in case, what happens if we have 3D? Same thing goes here. So basically, just for example, over here you have it in x and y. So if it's a 3D, assuming that we add another z component to it, all right, so it's just going to be the same, all right, only that when you have my r bar, I'll have xt, yt, and then comma zt. Same goes for my r prime magnitude. I'll just add another component, which is plus dz over dt square. All right, so I hope you have no confusion with this. And do note that just some different notation that we might have from time to time. Sometimes you will see something like this for its line integral, ft.ds. It's actually just equivalent to our f.dr or f.dl. So it doesn't matter what the question actually indicates it, because after all these dl and all that, those are just variables, all right? But as long as you understand the important concept, then that should be fine, okay? We are going to do an example based on this, but I've already parked it in the other video. So if you want to look at how to solve a question based on this line integral equation that's being highlighted in a box, so you can click to the other video now. You can click the other video now and see how it goes, and then resume back on this video, because this video will just be a summary of the whole chapter. All right, so there are one or two examples regarding this one. All right, so do have a look at it. Okay, so now next we want to move on to, so if you look at it earlier, we have covered this 2D and 3D form, right? We have looked at the fundamental theorem. Fundamental theorem is something that I just want to emphasize a little bit here, because we have looked at 2D, 3D, all right? Basically, the important formula that you need to remember will be this one here, all right? The one in the box. I'll just put this note here. So, some fundamental theorems that you want to remember, all right? So, if we have closed path, all right, the term closed path, where we have our line integral being performed, if we're performing line integral, because remember earlier from what you saw, it's something like this, right? You can have a curve like this, all right, and then, but it's not closed path. This is an open path. Closed path just basically means that the end, well, it's going to be closed, right? So if I extend this or whatever, say I have a line here from here onto all the way here, all right? So if we have a closed path where line integral is performed, we actually have another term for it. We call this circulation, all right? Just some terms that you need to remember, all right? And so that's one. Fundamental theorem 1. Let's see what else do you need to remember. Also, one thing that is very important, we also say that our f function is conservative if there is a function f such that my f bar is equals to my nabla of my f. All right, so f here is also what we call the potential function. Okay, so which means if my f bar is a gradient, so this, remember, is sort of your gradient. We have learned about this not too long ago, the gradient or the nabla. So if f bar is the gradient of potential function f, right, then f bar is what we call a conservative vector. All right, so basically what we need to know is that if we have my f bar equals to nabla of f, the gradient of f, then f is what we know as conservative vector. All right, now here comes the question. I'm just going to scroll this up a little bit since we talk about conservative. So here comes the question. How do we check? How do we know whether f bar is conservative or not? All right, so as long as it fulfills this criteria, all right, that first my f bar is a continuous vector field. So I think for this one it's pretty much self-explanatory. Continuous, you should know what is continuous by now, right? So which means that your f is just continuous. You do not have any break in between, or you do not have anything like this. All right, so anything that's continuous. So that's criteria number 1. For criteria number 2, all right, so I have the f, which means the line integral of my f, right, is independent of the path it takes. So what does it mean by independent? So remember, when we talk about independent, it basically means that if I have any curve, I can have this as the beginning point. I have a curve. Let's call this curve 1. All right, and it goes from this point all the way to this point. And I can also have another curve starting from the same point and the end point, and I'm going to call this C2. All right. So we see that the f dot dr, or which means the line integral, is independent if we have my line integral of C1 equivalent to my integral of C2. All right. So with any, and this applies to any curves of C1 or C2 whatsoever, as long as it has the same initial point and the same ending point. All right. And if my f dot dr here is independent of path, then it also means that the line integral of my f dot dr will be equivalent to 0 for every closed path. For every closed path C. Alright? These are just some terms for you to know. Probably will help you later and whatnot. Alright? So be familiar with all these terms here. Okay? So now that we have looked at fundamental theorem, if we look at the third one earlier, the third thing that we want to look at of the fundamental theorem is the curl. Alright? So, what do we know about curl exactly? Curl is what we say as the basic concept of it, yeah? Sorry. Basic concept of curl. Alright? So, if we perform or if we evaluate curl at certain point, it basically indicates the measure. The measure of how much direction of the vector f wraps around the point. Alright. Another way to look at it is, like, say you have your f vector here being the velocity field of a flowing fluid, for example. So curl f will then represent the tendency of your particles, of it comprising x, y, z, to rotate around the axis. Alright, at the points in the direction of your curl f. So that's why how much direction your f actually wraps around the point. So imagine that you see a swirl of water circling around a point. If you visualize that, that's pretty close. All right. And just how do we know more about curl? And what's this curl f basically? So let's say that we want to find a curl of a vector field f. Alright, and this f is given by its x component, y component, z component. I'm just going to write as that. So there again comes the formula. The curl of f is actually our gradient cross f bar. Alright, so this is a cross product. Like the one earlier, you actually saw a dot product. And how do we go about this? It's actually your I, your j, your k, and then remember the gradient. Gradient is given by your d of dx, d over dy, d over dz. And lastly, this part here would be basically just the coefficient of your x, axis, your y, and your z. And I'm just going to write a vertical line here just to indicate it. Alright, the curl. Okay, and I hope you still remember how to perform your cross product for this one, but we're definitely going to look through it in the class, so don't worry about that. And then what else do you need to know? Say if you know that just now we talked about conservative field, right? So if your f is a conservative vector field, another way for you to know that it is a conservative vector field, right? You can test it out using this curl f, where your curl f is actually 0. Alright? And we say that when we actually have the equation that satisfies this, we also say that your f is actually irrotational. Does it make sense? Because curl actually revolves around, like what I asked you to visualize, it's like circling how much how much your function actually wraps around, right? The direction of your function f wraps around the point. So you imagine like a swirling of circling of velocity of fluid, for example, wrapping around a certain point. So it sort of like rotates and all that. So if you talk about curl f being 0, all right, and this is one of the criterion that satisfies f being a conservative vector field, we also say that this is irrotational. All right. And then once you are clear with this, then move on to the last bit here. And what we have for the last bit is about your f dot ds versus your f of t dot ds. All right. So what do you see as the difference between these two? All right. Oops. Sorry again. The screen is just moving. So if you notice, if we're talking about f dot ds here, all right, so which means that your function is just of x, y, and z, all right? So I'm just going to write this down. I'll have function of f, y, z, and then remember, whatever that you saw earlier, you multiply it by dx over dt square plus dy over dt square plus dz over dt square. All right, don't forget the integral. So this is what it is for f dot ds, and let's have a look at this instead. If I have f dot t ds, so that basically means that your f bar here is actually in your vector form, right? So which means you will have to basically parameterize your equation first. That's where you get your f of xt, yt, zt, all right, dot your r prime t ds. Oh, sorry, it will then be dt over here. All right, so actually not much of a difference. Is actually exactly the same, only that the parameterization that happens and when you have your vector field, all right, so that's just going to be somewhat different, slightly different in that way. But no worry about this, since now you're clear. So if just to sum up whatever that we did, we first look at the line integral. We have the formula for my line integral, all right, and for the 2D and 3D, it's just working accordingly. If 3D, then we just add a component to it. You also learn some fundamental theorems about it being closed path. Circulation, what's circulation? By now you should recall what it is. How do we say whether f is conservative or not, right? And potential function, and then and how do we check if it actually satisfies this conservative field? That is when your f is actually continuous and is independent of its path. Next, we also learn about curl. All right, curl is basically just our nabla cross f. All right, and then lastly, how do we differentiate your f ds? How do we solve it when we have just a scalar function? And this is actually for our vector function. I'm sure we will look at this in other examples and all that. So if you're ready to do it, then please click on to other examples in the separate videos after this. All right, good luck.